Bit Simply 5. Learn, loop, evolve.
All right, let's just jump right into this explainer. If you write code, you know the drill. Managing complexity is literally half the battle. But when we start stacking these massive complex systems on top of one another, man, the underlying memory structure can sometimes turn into a complete labyrinth. So it brings up this really massive question. How do engineers actually combine complex software systems without completely crashing the program's memory? It's a super high-stakes engineering problem. Like, we want modularity, right? We definitely want to reuse code. But combining modular code, especially in a language like C++ that gives you absolute direct memory access, well, it can lead to catastrophic ambiguity if you aren't careful. To really get why this conflict happens, we're going to hit Section 1, Foundations of Object-Oriented Programming. Let's build those pillars first. You know, OOP has a really fascinating evolution. The academic research by Kiri Daniela Sanchez-Duran points out that this paradigm didn't just appear overnight. It actually emerged way back in the 1960s with Simula. Then it gained massive consolidation and mainstream adoption around 1995 with Java. And today, it is absolutely the backbone of contemporary software complexity. It's powering everything from modern Python and C# apps to massive video game engines and AI frameworks.
Now, one of the four main pillars of this whole paradigm is inheritance. This is what allows a derived class or a child class to acquire the properties of a base class, creating what we call an is-a relationship. Basically, think of it like this. A laptop is a computer. In the real engineering world, we almost never want to build from scratch if a proven foundation already exists, right? Inheritance solves these huge industrial problems by giving us reusability. You write the code once in the base class, and boom, use it everywhere. It gives you transitivity and extensibility, letting you add features without constantly rewriting proven foundational legacy code.
All right, so that sounds great in theory, but let's dive into Section 2, the mechanics of inheritance. We're going to look closely at the rules, memory, and execution.
Let's get a bit analytical here and look under the hood. Think of memory kind of like physical engineering real estate. When you inherit a class, the compiler doesn't just toss everything into a blender. No, the base class subobject is laid out first. It takes up its allocated block of memory, like a solid 4 bytes. And then it is followed immediately by the data members of the derived class. This specific physical layout is exactly why a pointer that's pointing to a base class can safely point to a derived object, because to the computer, the beginning of that memory block looks exactly like the base class. It's pretty clever.
And then we have this matrix. Think of it as your architectural access control list. It details exactly how your public, protected, and private gatekeepers shift around during different types of inheritance. Notice that bottom row? Private members of a base class are technically inherited, meaning they literally physically exist in that memory layout we just looked at, but they become completely inaccessible to the child class directly. You have to go through approved public or protected channels to get to them. It's honestly a brilliant way to protect the integrity of the base code.
But hey, memory isn't just about physical space, right? It's also about time. The order of execution is absolutely critical here. When you build an object, you build the foundation first. So the base class constructor executes, then the derived. But when you tear it down, it's the exact reverse. The derived destructor goes first, followed by the base. And listen, here is a massive engineering warning straight from our sources. If you're manually managing memory with pointers, you absolutely must use a virtual destructor in the base class. If you don't, and you delete a derived object via a base pointer, only the base portion gets cleaned up, and you are left with a massive, nasty memory leak. Nobody wants that.
Okay, so everything is going great with our code reuse. We're saving time, our memory is totally organized. Until we hit Section 3, confronting the diamond problem. Let's look at the danger of multiple inheritance.
Because C++ allows a child to have more than one parent, which we call multiple inheritance, this dramatic tension pops up. What actually happens when two parent classes inherit from the exact same blueprint? Well, it creates the scenario where the compiler actually just panics, because multiple inheritance paths are leading back to a single root.
Let's build a realistic automotive simulation to really see this in action. Imagine you have a generic root-based class called engine. Okay. Then we create an electric class that inherits from engine. We also create a petrol class that inherits from engine. So far, so good. But then we create a hybrid car, And naturally, our hybrid car needs to inherit from both electric and petrol. Because both of those parents inherited from engine, the hybrid car is now literally duplicating the generic engine base class in its physical memory layout. If you map it out, it forms the shape of a diamond.
And suddenly, boom, the ambiguity error hits. Just like Geeks for Geeks documents, you try to call a standard base function and the compiler completely freezes. It literally spits out, error, requests for member is ambiguous. Why? Well, because our hybrid car has two physical copies of the engine's members sitting in its memory block. One from the electric side, one from the petrol side. The compiler just throws its hands up. It has absolutely no idea which physical copy of the engine you actually want to talk to.
Thankfully, C++ equips us with some specific technical weapons to deal with this. Welcome to Section 4, Resolving Inheritance Ambiguity. Let's climb out of this hole.
So we basically have two main ways to handle this mess. Over on the left, we can manually patch the ambiguity using the scope resolution operator. That's those two colons. You're explicitly telling the compiler, hey, use the print function specifically from parent B. And sure, it works, but it's kind of just a band-aid. On the right, though, we have the ultimate fix, virtual inheritance. Virtual inheritance doesn't just point to the right function, it structurally corrects the memory layout itself.
Check this out. By simply adding the keyword virtual when electric and petrol inherit from engine, we completely change the rules. We're basically telling the compiler, hey, if someone inherits from both of us down the line, only give them one single shared instance of the engine-based class. So now the hybrid car is guaranteed to share only one unified engine instance in memory. The diamond is resolved, the whole shebang is fixed, and there's absolutely no more ambiguity.
Which brings us to Section 5, Real-World Engineering Applications. Let's talk about why this all actually matters.
Because resolving these compiler issues isn't just some academic exercise to help you pass a coding interview, right? It's a fundamental necessity for industrial-scale software development. Whether you're building highly realistic video games in the Unity engine, managing massive corporate ERP and CRM systems, developing artificial intelligence, or running the exact type of automotive software simulations we were just talking about, you rely on inheritance. Understanding how memory structure works and utilizing tools like virtual inheritance allows you to safely modularize massive code bases so they don't just collapse under their own weight.
As the academic research from Kiri Daniela Sanchez Duran highlights here, despite having a pretty steep learning curve, a structured, object-centric design philosophy is absolutely your greatest asset against software complexity. It's exactly what enables the creation of modular, reusable, and scalable systems. When you get this right, you are building digital infrastructure that can literally last for decades.
So I'm going to leave you with this final thought today. How will you architect your next complex system to prevent the diamond from shattering? The next time you sit down to design a system, just remember, true engineering isn't only about writing code that works on the surface. It's really about mastering the physical memory underneath.